Welcome back to Scientific Discovery Hub, where we unravel the universe's most mind-bending mysteries. Have you ever wondered how something as massive as a comet could hide inches, one of the busiest, brightest regions of the cosmos? Today, we're diving into the astonishing story of 3I Atlas, an interstellar comet that managed to evade detection for eons, right behind the blazing veil of the Milky Way's Galactic Center. Picture this, a frozen wanderer, hurtling through space at 58 kilometers per second, fast enough to escape the sun's gravity entirely. Yet for years, 3I Atlas remained hidden inches plain sight, cloaked by the chaos of stars, gas and dust at the heart of our galaxy. How did it slip past our telescopes? And what secrets does it carry about its origins, billions of light years away? In this video, we'll break down the cosmic detective work that finally uncovered this interstellar intruder. Starting with the Galactic Center veil, we'll explore how the Milky Way's own brilliance masked 3I Atlas's faint glow. Then we'll follow its hyperbolic escape route, a trajectory so extreme it defies our usual rules of orbital mechanics. Using cutting-edge algorithms and star maps, scientists traced its path back to the Milky Way's thick disk, a region older than our solar system itself. Along the way, we'll decode its chemical fingerprint, revealing clues about its alien birthplace, and even peek at how Mars rovers might help us watch its dramatic solar showdown, Inches 2025. But 3I Atlas isn't just a cosmic curiosity. It's a challenge to our understanding of the universe. Why did it arrive from the wrong direction? Could it hold building blocks of life? And what else is hiding Inches the galaxy's busy corners? Whether you're a seasoned stargazer or just curious about the latest scientific breakthroughs, this video will take you on a journey through interstellar detective work, galactic archaeology, and the limits of human observation. So hit play, subscribe for more deep dives into the wonders of science, and let's uncover the secrets of 3I Atlas together. Stay curious and let's explore the cosmos, one mystery at a time. In the vast expanse of the Milky Way, the Galactic Center stands as both a beacon and a veil, a region of staggering complexity that conceals as much as it reveals. Here, the sky is ablaze with the light of countless stars, their collective glow forming a radiant haze that drowns out the faint whispers of distant travelers. It is Inches this luminous chaos that 3I Atlas, an interstellar comet of profound antiquity, slipped past the watchful eyes of astronomers for weeks before finally being detected. The sheer density of stars and interstellar dust Inches this region rendered the comet nearly invisible. Its delicate trail of gas and dust lost Inches the cacophony of celestial brilliance. Yet, once glimpsed, 3I Atlas became a revelation, an interstellar visitor bearing secrets from the farthest reaches of the galaxy. The Milky Way's core is not merely a backdrop of beauty. It is a dynamic crucible of cosmic forces. Its gravitational tides stir the fabric of space, shaping the trajectories of stars, gas clouds, and even rogue objects that drift through its domain. Within this maelstrom, 3I Atlas emerged from the depths of interstellar space, its journey across the void guided by unseen currents. The comet's arrival marked a rare moment of clarity amid the Galactic Center's overwhelming radiance, a fleeting glimpse into the mysteries of the universe beyond our solar system. Its path, traced by the light it emitted as it neared the sun, revealed an object unlike any seen before, one that had traveled for eons through the galactic dark, untouched by the familiar rhythms of the solar system. Yet the significance of 3I Atlas extends beyond its mere existence. Its discovery challenges our assumptions about the nature of interstellar objects and the ways Inches which we detect them. If such a massive and active comet could remain hidden for so long, what else might be lurking Inches the shadows of the cosmos, waiting for the right moment to be seen? The Galactic Center is a realm of extremes, where the density of stars reaches unparalleled levels, and the interplay of radiation, magnetic fields, and gravitational forces creates a cosmic tapestry of complexity. It is Inches this tumultuous environment that 3I Atlas spent a significant portion of its journey before entering the solar system, its presence obscured by the sheer brilliance of the region. The Milky Way's core is home to over 100 billion stars, many of which emit intense ultraviolet and X-ray radiation that bathes the surrounding space. This radiation, combined with the dense interstellar medium composed of gas and dust, creates a formidable barrier for faint objects like comets. Against such a backdrop, 3I Atlas's faint glow was nearly indistinguishable from the ambient light of the galaxy. When 3I Atlas was finally observed, it was already at a distance of 4.5 astronomical units (AU) from the Sun, nearly half the distance from the Sun to Pluto. Yet it had only recently begun to interact with the solar system's gravitational. At that point, the comet was traveling at an incredible speed of 61 kilometers per second, relative to the Sun, a velocity that immediately raised suspicions among astronomers. The object's trajectory, when plotted against the positions of other celestial bodies, revealed a path that deviated significantly from the typical elliptical orbits of solar system comets. Instead, it followed a hyperbolic trajectory, indicating that 3I Atlas was not gravitationally bound to the Sun and was destined to escape the solar system entirely. This revelation marked it as the third confirmed interstellar object to visit our cosmic neighborhood, following the enigmatic 1I Oumuamua Inches 2017. The comet's approach to the solar system was not one of chance but of necessity, dictated by the gravitational tides of the Milky Way. As it traversed interstellar space, 3I Atlas was influenced by the gravitational pull of distant stars and the overall motion of the galaxy itself. Its path brought it toward the solar system's outer edges, where it gradually accelerated due to the Sun's gravity. Before beginning its swift departure, the comet's interaction with the solar system was brief but profound, offering scientists a rare opportunity to study an object that had traveled from a distant corner of the galaxy, carrying with it the chemical fingerprints of its interstellar origins. The discovery of 3I Atlas challenges a fundamental assumption in astronomy, that the most extraordinary objects in the universe are the easiest to detect. In truth, the cosmos is replete with wonders that elude observation, precisely because they exist in places where our instruments struggle to distinguish the signal from the noise. The Galactic Center, with its overwhelming density of stars and interstellar material, serves as a prime example of such a region. Here, the very brilliance of the Milky Way's heart becomes a veil, masking the faint traces of interstellar travelers like 3I Atlas. This realization forces us to confront the limitations of our current observational methods and to question how many other interstellar objects might be hidden in plain sight, their signals drowned out by the cosmic cacophony. This phenomenon raises profound implications for our understanding of interstellar exploration. If 3I Atlas, a relatively large and active comet, could evade detection for so long, what might be lurking in the galaxy's other crowded regions? Could there be entire populations of interstellar objects, asteroids, comets, or even rogue planets that have yet to be catalogued? The answer may lie in refining our observational strategies, perhaps by focusing on regions that are traditionally overlooked due to their brightness or complexity. The Milky Way's Galactic Center, for instance, represents a frontier of discovery that demands innovative approaches. By developing technologies capable of sifting through the noise of such dense star fields, we may uncover interstellar objects that carry clues to the formation and evolution of planetary systems far beyond our own. Moreover, the story of 3I Atlas underscores the importance of serendipity in scientific discovery. Its detection was made possible not only by advanced telescopes, but also by the collaborative efforts of both professional and amateur astronomers. This interplay between cutting-edge technology and human curiosity highlights the value of diverse perspectives in unraveling the universe's mysteries. As we continue to refine our tools and techniques, the lessons learned from 3I Atlas may guide us toward new discoveries that further expand our understanding of the cosmos and our place within it. To understand how 3I Atlas managed to slip past the Sun's gravitational embrace, we must first examine the nature of its trajectory. Unlike the comets native to the solar system, which follow elliptical paths that bring them back on regular cycles, 3I Atlas is on a one-way journey. Its hyperbolic trajectory, an open curve rather than a closed ellipse, reveals that it is not bound to the Sun and will never return. This is not a mere quirk of orbital mechanics. It is a defining characteristic of interstellar objects. The Sun's gravity, while immense, cannot hold onto something that arrives with a velocity exceeding the escape threshold. In 3I Atlas's case, its speed relative to the Sun is an astonishing 58 kilometers per second, far above the 42 kilometers per second needed to break free from the Sun's gravitational pull at its current distance. This hyperbolic excess velocity is the key to its interstellar identity. The physics governing such a trajectory begins with the concept of specific mechanical energy. For an object to maintain a stable orbit around the Sun, its specific mechanical energy must be negative, meaning it is gravitationally bound. However, for an object like 3I Atlas, the specific mechanical energy is positive, indicating that it possesses more kinetic energy than is required to remain inches a closed orbit. This surplus energy allows it to follow a hyperbolic path, slingshotting through the solar system before departing into the interstellar void. The Sun's gravity does not trap 3I Atlas. Instead, it briefly alters the comet's course, accelerating it slightly as it passes through the inner solar system. This acceleration is a consequence of the Sun's gravitational field, which imparts additional momentum to the comet, ensuring its departure from the solar system is swift and unimpeded. By tracing 3I Atlas's path backward inches time, astronomers have determined that it entered the solar system from the direction of the Galactic Center. This origin suggests that the comet's journey through interstellar space was not random, but influenced by the gravitational tides of the Milky Way. The fact that it followed such a precise trajectory toward the solar system indicates that it was not flung outward by a violent stellar encounter, but rather drifted along the natural currents of the galaxy. As it continues its outbound path, it will eventually cross the heliosphere, the boundary where the Sun's influence wanes, and venture into the cold, dark expanse of interstellar space, carrying with it the echoes of a distant past. Beneath the vast tapestry of the night sky, where constellations whisper tales of ancient civilizations and galaxies swirl inches silent symphonies, a solitary traveler emerged. In the quiet hours of 1 July 2025, at the Atlas Observatory inches the arid expanse of Rio Hurtado, Chile, humanity's gaze caught a fleeting glimpse of something extraordinary, a comet hurtling through the inner solar system at a velocity of 58 kilometers per second, faster than any natural object born of our cosmic neighborhood. This was 3I Atlas, a celestial nomad, unshackled from the gravitational embrace of the Sun. Its arrival was not a mere accident, but a profound declaration. The universe is alive with wanderers, each carrying secrets etched inches the primordial ice of distant stars. What makes 3I Atlas so remarkable is not merely its speed, but the trajectory it follows, a hyperbolic path that curves outward, never to return. Unlike the elliptical orbits of planets and comets bound to the solar system, this comet's journey is one of perpetual departure. It does not belong here. It is a relic from another star system, a messenger from the farthest reaches of the galaxy. As it glides past the orbits of Earth and Mars, its icy nucleus radiates a quiet defiance of the cosmic order we once believed immutable. Yet, for all its grandeur, 3I Atlas is a fragile witness to the cosmos. Its nucleus, veiled inches a coma of gas and dust, is a mosaic of carbon dioxide, water ice, and traces of cyanide, a chemical fingerprint hinting at the volatile history of its birthplace. It is the third interstellar object ever observed, joining the ranks of 1I Oumuamua and 2I Borisov. Yet, unlike its predecessors, 3I Atlas carries a unique legacy. Traced backward inches time, its path leads to the Milky Way's thick disk, a realm of ancient stars where the universe's earliest generations still burn. This comet, if the calculations hold, may be older than our own solar system, a relic of a time when the cosmos was young and wild. To understand 3I Atlas is to unravel a thread inches the vast fabric of existence. What forces propelled it into the void? How did it survive the crucible of interstellar space for billions of years? And what does its arrival tell us about the nature of our place inches the cosmos? These questions, like the comet's tail, stretch toward the unknown, inviting us to peer beyond the familiar and into the infinite. At the heart of 3I Atlas's mystery lies its hyperbolic trajectory, a mathematical curve so elegant inches its defiance of the familiar. To grasp its significance, one must first revisit the fundamental principles of orbital mechanics. In the solar system, objects follow elliptical paths dictated by the sun's gravity. Their motion a delicate balance between inertia and gravitational pull. Planets, asteroids, and comets alike are bound to these loops, their fates sealed by the invisible threads of celestial mechanics. But 3I Atlas is different. Its path is not a closed ellipse, but an open hyperbola, a curve that arcs away from the sun and vanishes into the interstellar abyss. Why? Because its velocity exceeds the escape velocity of the solar system, calculated at 58 kilometers per second. This speed is sufficient to overcome the sun's gravitational grip, allowing the comet to traverse the solar system as a transient guest, rather than a permanent resident. Such trajectories are rare inches our cosmic backyard. They require an external force to impart the necessary energy. For 3I Atlas, that force must have originated elsewhere. Perhaps a violent encounter with a giant planet inches its home system, a cataclysmic collision between stars, or the explosive fury of a supernova. Whatever the cause, the result is a comet that does not belong to the solar system, yet briefly shares its stage. Hyperbolic orbits are governed by the same laws that dictate the motion of planets, yet they represent a boundary condition, inches celestial mechanics. Now, imagine a ball thrown straight upward. If it gains enough speed to escape Earth's gravity, it will not fall back. Similarly, 3I Atlas's velocity ensures it will not return. Its journey is a testament to the dynamic interplay of forces inches the universe, a reminder that even the most stable systems can produce outliers, objects that defy categorization. This trajectory also raises profound questions about the origins of interstellar objects. Unlike asteroids or comets native to the solar system, which originate from the Kuiper Belt or Oort cloud, 3I Atlas hails from interstellar space. Its path, traced back through the stars, points to the direction of Sagittarius, near the Milky Way's Galactic Center. Yet its approach is not random. The comet's velocity vector suggests it is part of the thick disk population, a group of stars and objects that move inches inclined orbits relative to the galactic plane. This distinction is critical, for it hints at a cosmic history spanning billions of years, a timeline that predates the formation of our solar system. Understanding 3I Atlas's hyperbolic path requires more than equations. It demands a reimagining of our cosmic neighborhood. The solar system is not an isolated sanctuary, but a node inches a vast network of gravitational interactions. Interstellar objects like 3I Atlas are not anomalies, but inevitable consequences of the Milky Way's chaotic dance. Every star, every planet, and every comet is subject to the gravitational tides of the galaxy. And occasionally, these tides wrench objects free, sending them on journeys that span light years. As 3I Atlas hurtles toward perihelion, the closest point inches its path to the sun. It becomes a living paradox. It is both alien and familiar. A stranger inches the solar system's core, yet bound by the same physical laws. Its presence challenges our assumptions about the boundaries of our cosmic domain, reminding us that the universe is not a static collection of islands, but a fluid, interconnected web. To comprehend 3I Atlas's origins, we must rewind the clock of the universe by billions of years. The comet's trajectory, meticulously charted by observatories across the globe, reveals a journey that began inches the thick disk of the Milky Way, a region where ancient stars, forged inches the early epochs of the galaxy, drift inches slow, tilted orbits. Unlike the thin disk, which hosts younger stars like our sun, the thick disk is a relic of the galaxy's tumultuous youth, a place where stellar populations are older, richer inches dark matter, and poorer inches heavy elements. If 3I Atlas indeed hails from this region, its nucleus may contain materials untouched since the dawn of the cosmos, preserving the chemical signatures of an era when the universe was still learning to create complexity. The evidence supporting this hypothesis lies inches the comet's velocity components. When scientists decomposed 3I Atlas's hyperbolic excess velocity, into radial transverse mine faults, and vertical mine faults directions, they uncovered a striking pattern. The comet approached the solar system moving away from the galactic center at 51.0 kilometers per second. This motion places it firmly within the thick disk's kinematic profile, a population of objects that rarely venture into the thin disk's more orderly circular orbits. Such a trajectory suggests that 3I Atlas has spent eons navigating the gravitational turbulence of the galaxy, perhaps ejected from a distant planetary system by a catastrophic event. But what might have propelled this comet into the void? The possibilities are as varied as the cosmos itself. One scenario imagines a binary star system, where gravitational interactions between two suns destabilize the orbits of surrounding bodies, hurling some into interstellar space. Another posits a supernova explosion, whose shockwave could have scattered debris across the galaxy. More radically, some theorists speculate that 3I Atlas was born in the aftermath of a planetary collision, its fragments coalescing into a nucleus capable of surviving the harsh conditions of interstellar travel. Each hypothesis paints a different picture of violence and transformation, underscoring the chaotic beauty of cosmic evolution. Yet perhaps the most profound implication of 3I Atlas's origin lies in its age. Studies by Matthew Hopkins and Asta Taylor independently suggest that the comet could be between 3 and 14 billion years old, far older than the solar system's 4.6 billion year history. If accurate, 3I Atlas is a relic from an epoch when the Milky Way was still assembling itself, a time when stars were forming frenzied bursts, and the galactic disk was a turbulent sea of collisions and mergers. Such an ancient object carries within it the chemical fingerprints of the early universe, offering a rare glimpse into the raw materials from which planets and life may have emerged. The comet's composition, as revealed by the Hubble and James Webb Space Telescopes, adds further intrigue. Rich in carbon dioxide and laced with traces of water ice, carbon monoxide, and carbonyl sulfide, 3I Atlas's makeup diverges from many solar system comets, which typically contain higher proportions of water. This discrepancy hints at differences in the environments where such objects form, perhaps reflecting the unique conditions of its birthplace. The detection of cyanide gas and atomic nickel vapor, elements commonly associated with the destructive heat of stellar processes, raises questions about the comet's survival. How did it endure the radiation and cosmic rays of interstellar space for eons without disintegrating? Could its nucleus be encased in a protective layer of refractory material, shielding it from the universe's relentless forces? These mysteries are compounded by the comet's unexpected southern origin. Previous models predicted that most interstellar objects would arrive from the solar apex, the direction of the sun's motion through the local standard of rest. Instead, 3I Atlas came from the opposite hemisphere, a finding that challenges existing theories about the distribution of interstellar objects in the galaxy. Was this a statistical anomaly, or does it signal a hidden abundance of southern origin comets waiting to be discovered? The answer may lie in the limitations of our current observational tools. Southern hemisphere surveys are fewer and less sensitive than their northern counterparts, suggesting that 3I Atlas might be just one of many interstellar visitors lurking in the uncharted depths of the cosmos. As 3I Atlas continues its journey, its path offers a unique opportunity to probe the dynamics of the Milky Way. By analyzing its trajectory and velocity, astrophysicists can map the gravitational influences of nearby stars and dark matter, refining our understanding of the galaxy's structure. Moreover, the comet's interaction with the solar system, though brief, provides a natural experiment in how interstellar objects behave when subjected to the sun's heating. Will its coma brighten dramatically, or will it disintegrate under the pressure of solar radiation? These outcomes will not only inform models of comet evolution, but also shed light on the resilience of interstellar matter in the face of cosmic adversity. If 3I Atlas is a messenger from the galaxy's depths, then its journey is inscribed in the stars themselves. To trace its origins, we must read the heavens as an ancient navigator reads the waves, seeking patterns in the chaos. The comet's trajectory, a hyperbola stretching across the void, is a thread in the galactic tapestry, a clue to the gravitational currents that shaped its voyage. Yet the answers lie not only inches its motion, but inches the silent dialogue between stars, a conversation written inches their movements, compositions, and the unseen forces that bind them. The Milky Way, vast and intricate, is a living archive of cosmic history. Its spiral arms, halo, and thick disk are not static structures, but dynamic realms, constantly shifting under the influence of dark matter, stellar winds, and the gravitational tides of neighboring galaxies. Every star, every nebula, every rogue planet contributes to this symphony of motion. 3i Atlas, inches its brief passage through the solar system, has become a participant, inches this grand design. A fleeting note, inches the galaxy's eternal song. To understand where it came from, we must look beyond individual stars and consider the galactic architecture that governs their movements. The thick disk, from which 3i Atlas likely originated, is a relic of the Milky Way's violent youth, a region where ancient stars drift inches inclined orbits, their paths tilted relative to the galactic plane. These stars, enriched by the remnants of long-dead supernovae, carry with them the chemical signatures of the universe's earliest epochs. If 3i Atlas shares their heritage, then its nucleus may hold secrets about the conditions that preceded the formation of our solar system. Yet the galaxy is not a passive backdrop to this story. It is a dynamic engine, its gravitational field shaping the trajectories of interstellar objects. Like 3i Atlas, the comet's vertical velocity component, its upward motion through the galactic plane, suggests it is not merely a wandering fragment, but a participant inches the Milky Way's complex gravitational dance. Perhaps it was flung into the void by a close encounter with a massive star, or perhaps it was born inches the turbulent environment of a star-forming region, where collisions and gravitational slingshots are commonplace. The path of 3i Atlas is not just a record of its past, but a map for the future. As astronomers refine their models of the galaxy's gravitational tides, they may uncover new interstellar objects hiding inches plain sight, their trajectories similarly shaped by the unseen forces of the cosmos. With each discovery, the veil between our solar system and the wider universe grows thinner, revealing a cosmos teeming with connections. And so, as 3i Atlas fades from view, its hyperbolic path serves as a reminder. The universe is not a collection of isolated worlds, but a vast interconnected web. Every object, no matter how distant, is part of a greater whole. Its journey a thread inches the infinite loom of existence. The next chapter inches this story lies not inches the comet itself, but inches the stars that guide its way, a journey we are only beginning to comprehend. In the vast, silent expanse of the cosmos, a traveler has arrived, a visitor from another star system, bearing secrets of distant worlds and ancient epochs. 3i Atlas, the third confirmed interstellar object to traverse our solar system, is more than a fleeting point of light inches the night sky. It is a relic of interstellar history, a frozen monument to processes that shaped galaxies long before the birth of Earth. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, telescope inches Chile, this enigmatic comet entered the inner solar system at a blistering speed of 61 kilometers per second, hurtling toward the sun, along a hyperbolic path that defies the gravitational embrace of our star. Unlike the countless asteroids and comets born within the solar system, 3i Atlas is a stranger. Its trajectory, unbound by the sun's pull, reveals its origin beyond the confines of our stellar neighborhood, yet even inches its brief passage. This interstellar wanderer offers a glimpse into the hidden architecture of the Milky Way, the ancient dance of matter across eons, and the possibility that the universe is a tapestry woven with threads from distant stars. What makes 3i Atlas extraordinary is not merely its origin, but its story. It is the first interstellar object observed to exhibit cometary activity, the sublimation of ice, and the release of gas and dust as it journeys through the solar system. This activity, driven by the sun's heat, transforms it from a cold, dark body into a glowing apparition, its coma and tail betraying the presence of volatile compounds. Observations by the Hubble Space Telescope and the James Webb Space Telescope have unveiled a composition unlike any native solar system comet, a wealth of carbon dioxide, traces of water ice and carbon monoxide, and even cyanide gas and atomic nickel vapor. These ingredients paint a picture of a world forged inches a different stellar cradle, one where the chemistry of life's building blocks may have taken root under alien conditions. But 3I Atlas is not just a scientific curiosity, it is a bridge to the unknown. By tracing its path, astronomers rewind the clock of the cosmos to uncover the origins of this traveler, and perhaps the origins of ourselves. In doing so, they grapple with profound questions. How many such interstellar visitors have passed through the solar system unnoticed? What do their trajectories tell us about the dynamics of galaxies and the distribution of planetary systems? And what might their ancient histories reveal about the universe's capacity to create complexity, even inches the void between stars? To unravel the story of 3I Atlas, astronomers turn to the language of orbital mechanics, a discipline that translates the motion of celestial bodies into mathematical poetry. Using precise astrometric measurements from the Atlas telescope and follow-up observations from the Zwicky Transient Facility, the Hubble Space Telescope, and ground-based observatories, scientists reconstructed the comet's path with remarkable clarity. The key lay inches its hyperbolic trajectory, a curve so sharp that it could not have been influenced by the gravity of any solar system planet. Instead, 3I Atlas's motion betrayed its interstellar heritage, its velocity exceeding the escape speed of the sun. The comet's journey was decoded by analyzing its velocity vector inches, 3 dimensions. Radially, it approached the solar system from the direction of the constellation Sagittarius, near the Galactic Center, a region teeming with ancient stars. Transversely, its sideways motion carried it across the plane of the Milky Way, while vertically, it ascended above the galactic disk, its path inclined at a steep angle. These components, when combined, revealed a critical insight. 3I Atlas hailed from the Milky Way's thick disk, a diffuse and ancient layer of the galaxy where stars move inches, chaotic orbits, and metals are scarce. Unlike the thin disk, which hosts younger stars like our Sun, the thick disk is a repository of primordial material, dating back to the early formation of the galaxy. The discovery was startling. Previous interstellar visitors, 1I Oumuamua, inches 2017, and 2I Borisov, inches 2019, had originated from the northern celestial hemisphere, aligning with predictions that more interstellar objects would be detected inches that direction due to the sun's motion through the galaxy. Yet 3I Atlas broke this pattern, emerging from the south, a region where telescopes had struggled to detect such objects. This anomaly hinted at a deeper truth. The distribution of interstellar material inches the galaxy may not conform to expectations, and southern origin comets could be far more common than once believed. By decomposing the comet's velocity into its radial, transverse bias volts, and vertical bias watts components, researchers calculated its trajectory with precision. The radial component, at 51.0 kilometers per second, indicated that 3I Atlas was moving away from the galactic center at the time of its arrival. Its vertical velocity, Pons 18.5 kilometers per second, suggested it was ascending through the galactic plane, a motion consistent with the thick disk's population of older stars. These numbers painted a portrait of an object born inches a stellar nursery billions of years ago, ejected from its home system by gravitational forces, and now adrift through the cosmic ocean. The study of 3I Atlas is more than a pursuit of origins. It is an exercise in galactic archaeology. By decoding the comet's trajectory, scientists unearth clues about the structure and evolution of the Milky Way. The thick disk from which 3I Atlas emerged is a relic of the galaxy's violent youth. Formed approximately 10 billion years ago, it is a remnant of mergers between smaller dwarf galaxies and the chaotic accretion of gas that built the Milky Way. Stars inches the thick disk move inches highly inclined orbits, their paths skewed relative to the galactic plane, a testament to the gravitational upheavals that shaped the galaxy. For 3I Atlas to originate from this region, it must have formed inches a protoplanetary disk around a star that has long since died. Its icy nucleus preserved inches the frigid vacuum of interstellar space. The implications of this finding are profound. If 3I Atlas is representative of a larger population of interstellar comets, then the thick disk may be a crucible for the formation of such objects. Its low metallicity environment, where heavy elements like carbon and oxygen are less abundant than inches the thin disk, suggests that the comet's composition reflects the primordial conditions of its birthplace. The detection of carbon dioxide and cyanide gas inches its coma supports this hypothesis, as these molecules are common inches cold, metal-poor regions of space. Moreover, the presence of atomic nickel vapor, a rare compound inches solar system comets, hints at chemical processes unique to interstellar environments. Yet the story of 3I Atlas is not solely one of isolation. Its journey through the solar system raises questions about the role of the Milky Way as a cosmic sieve. Could the galaxy's gravitational field act as a filter, capturing or deflecting interstellar objects based on their trajectories? The comet's hyperbolic excess velocity of 58 kilometers per second suggests that it has not interacted significantly with other stars, but its vertical motion through the galactic plane implies a history of encounters with unseen forces. Did 3I Atlas originate from a binary star system, where gravitational tides could have expelled it, or was it ejected by a dying star's final convulsions, hurled into the interstellar void as its host system collapsed? These questions are not confined to 3I Atlas alone. Every interstellar object that traverses the solar system is a messenger from the depths of space, carrying information about the conditions of its birthplace and the mechanisms that shaped it. By studying their trajectories, compositions, and ages, astronomers hope to reconstruct the evolutionary history of the galaxy and the diversity of planetary systems that populate it. 3I Atlas, with its ancient lineage and southern origin, challenges existing models and invites speculation about the asymmetry of interstellar traffic. Is our solar system a crossroads for comets from all directions? Or does it sit on the edge of a galactic highway, where most interstellar travelers come from one corner of the Milky Way? The answers lie inches the data. AMPA's July 2025 study by Matthew Hopkins and collaborators estimated that 3I Atlas is between 7.6 and 14 billion years old, placing it inches the same epoch as the earliest stars inches the thick disk. This age is staggering, over twice the age of the solar system, which formed 4.6 billion years ago. Such an object predates the formation of the Sun, the Earth, and the entire planetary system we call home. It is a relic from the dawn of the galaxy, a time when the Milky Way was young and violent, and the first stars ignited inches the darkness. An independent analysis by Asta Taylor and Darrell Seligman corroborated this conclusion, narrowing the comet's age to 311 billion years. Together, these studies underscore the uniqueness of 3I Atlas. It is not merely an interstellar object, but the oldest known comet inches human history. Its survival over such a vast timescale is a testament to the resilience of icy bodies inches the interstellar medium. Shielded from stellar radiation and gravitational perturbations, these objects drift silently through the cosmos, waiting for the rare encounter that propels them into the light of a distant star. The thick disk is not merely a spatial location. It is a temporal vault, preserving the echoes of the galaxy's earliest days. To comprehend the age of 3I Atlas, we must peer into the layers of the Milky Way, where the oldest stars, those born inches the aftermath of the Big Bang, linger inches slow, looping orbits. These stars, enriched with heavy elements from supernovae and neutron star mergers, are the foundation upon which the modern galaxy was built. 3I Atlas, originating from this ancient stratum, is a time capsule, its nucleus a frozen snapshot of conditions that existed billions of years before the Sun's birth. But how can we translate the comet's trajectory into a timeline? The answer lies inches the kinematics of the thick disk. Stars inches this region move at higher velocities relative to the galactic center and exhibit greater vertical motion, a consequence of the galaxy's turbulent youth. By comparing 3I Atlas's velocity components to those of nearby stars, astronomers infer that the comet belongs to this population, its motion mirroring the chaotic dance of thick disk stars. This connection allows researchers to estimate the comet's age by extrapolating the typical lifetimes of thick disk stars, which are generally older than 7 billion years. However, the thick disk is not a static entity. Over time, gravitational interactions with spiral arms and satellite galaxies have stirred its contents, scattering stars and interstellar material across the galaxy. 3I Atlas's trajectory suggests it has navigated these disturbances without being captured or disrupted, a feat that speaks to its robustness. Yet, even the most resilient objects are subject to the inexorable flow of time. As the galaxy evolves, the thick disk will gradually merge with the thin disk, diluting its ancient signature. 3I Atlas then is not just a witness to the past, it is a harbinger of the future, a reminder that the Milky Way is ever-changing, its history written inches the motions of its inhabitants. In the next segment, we will delve deeper into the age of 3I Atlas, exploring how its journey through the solar system illuminates the cosmic clock of the Milky Way. By linking the comet's interstellar heritage to the galaxy's evolutionary timeline, we begin to grasp the profound interconnectedness of all things. The stars, the comets, and the invisible forces that bind them together inches the grand design of the universe. In the vast, silent expanse of the cosmos, where time stretches into eons and distances defy comprehension, a traveler arrived. On 1 July 2025, nestled inches the arid skies of Rio Hurtado, Chile, the asteroid terrestrial impact last alert system, ATLAS, telescope captured a fleeting spark, a point of light, traversing the heavens at an astonishing 61 kilometers per second. This was no ordinary visitor. Designated A11 Pel 3Z, and later named 3I Atlas, it became the third interstellar object ever observed to breach the solar system's borders, following the enigmatic 1I Oumuamua and the more recent 2I Borisov. Yet 3I Atlas carried secrets older than our own celestial neighborhood, secrets etched into the fabric of the Milky Way itself. Its arrival stirred a profound sense of wonder among astronomers and dreamers alike. Here was a wanderer from the depths of interstellar space, hurtling through the void with a speed too great to originate from our solar system. Its hyperbolic trajectory, a cosmic slingshot beyond the gravitational embrace of the Sun, confirmed its extraterrestrial provenance. But 3I Atlas was not merely a speeding rock or ice ball. It was a comet, a dynamic world of frozen gases and ancient dust, glowing faintly as it danced with sunlight. In its wake, it left trails of carbon dioxide, water vapor, and even traces of cyanide and nickel. Chemical whispers from a stellar nursery long vanished. As scientists peered deeper into its nature, they realized they were not just observing an object, they were glimpsing a fossil of the galaxy's youth, a relic from an epoch when the Milky Way was still young and wild. Yet the story of 3I Atlas is more than a tale of discovery. It is a testament to humanity's unyielding curiosity, our drive to unravel the mysteries of the cosmos. For inches every starry night, there lies a question. Are we alone inches the universe? And if not, what stories do these interstellar visitors bring to us? Like messengers from distant realms, 3I Atlas, with its ancient origins and fleeting passage, invites us to ponder our place, inches the grand tapestry of existence, reminding us that the universe is far stranger and far more interconnected than we dare imagine. To understand 3I Atlas's journey is to trace the invisible threads of gravity, velocity, and time that bind the cosmos together. When the comet entered the inner solar system, it was already a ghostly figure, moving at a hyperbolic excess velocity of 58 kilometers per second relative to the Sun. This speed, faster than anything originating within our planetary system, was the key to its interstellar identity. Unlike asteroids or comets born inches the Kuiper belt or Oort cloud, 3I Atlas did not fall under the Sun's gravitational dominion. Instead, it followed a trajectory that bent sharply around the solar system, a cosmic flyby that would carry it back into the interstellar void. The mathematics of its path revealed its true nature, with an orbital eccentricity exceeding 1, a hallmark of hyperbolic motion. 3I Atlas's closest approach to the Sun, perihelion, would occur on 29 October 2025 at a distance of 1.36 astronomical units, AU. This placed it between Earth and Mars, yet it would not linger. Its velocity ensured it would escape the solar system entirely, its journey spanning millennia before it encountered another star. Such trajectories are rare, requiring precise alignment of gravitational forces and velocities to fling an object from one planetary system to another. For 3I Atlas, this meant it had originated from a distant corner of the Milky Way, where the gravitational tides of ancient stars sculpted its path. But what of its composition? As 3I Atlas approached, telescopes across the globe turned their gaze toward this interstellar intruder. The Hubble Space Telescope, with its razor-sharp vision, detected a coma, a shroud of gas and dust surrounding the nucleus, suggesting a diameter of less than 1 kilometer. The James Webb Space Telescope, peering into infrared wavelengths, uncovered a startling truth. 3I Atlas was rich inches carbon dioxide, a compound far more abundant inches, some solar system comets, alongside water ice, carbon monoxide, and carbonyl sulfide. These molecules painted a picture of a body forged inches a cold, chemically complex environment. Meanwhile, the Very Large Telescope revealed emissions of cyanide gas and atomic nickel, elements rarely seen inches such quantities outside our own system. Together, these findings hinted at a parent star system unlike our own, one where the building blocks of life might have taken different forms. Yet, even as scientists marveled at these discoveries, they faced a challenge. 3I Atlas was faint, with an apparent magnitude of no brighter than 11.5. It remained invisible to the naked eye, and elusive even to amateur astronomers. Only large telescopes and robotic observatories could track its slow progress across the night sky. Its path took it through the crowded star fields near the Galactic Center, a region so dense with stars that distinguishing the comet from background light required precision and patience. From Sagittarius to Libra, 3I Atlas traced an arc of light across the constellations, a silent witness to the universe's grandeur. To trace 3I Atlas's origin is to embark on a journey through time. Back to the dawn of the Milky Way, the comet's trajectory, meticulously reconstructed by astronomers, pointed toward the southern celestial hemisphere, inches the direction of the galactic center. This was no accident. The vertical component of its velocity, 18.5 kilometers per second upward from the galactic plane, placed it firmly inches the thick disk, a cosmic layer older and more diffuse than the thin disk, where our solar system resides. The thick disk, a puffed-up region of the galaxy, is home to stars billions of years older than the Sun, their light tinged with the signatures of an era when the Milky Way was still assembling itself from primordial gas clouds. If 3I Atlas indeed hailed from this region, it could be 7 to 14 billion years old, far older than the 4.6 billion-year-old solar system. This revelation sparked a cascade of questions. How could an object endure for such an immense span of time without succumbing to the violent collisions and gravitational tides of interstellar space? What kind of stellar cradle nurtured it, and what secrets did it carry from that ancient epoch? The comet's chemical composition offered tantalizing clues. Its abundance of carbon dioxide and scarcity of water ice suggested a formation environment colder and drier than the outer solar system, perhaps inches the shadow of a dying red giant, or within the frigid reaches of a protoplanetary disk disrupted by stellar encounters. The presence of cyanide and nickel vapor hinted at processes unique to its home system, where the chemistry of life's precursors might have unfolded differently. Even more intriguing was the possibility that 3I Atlas's age implied a history of interactions with other stars. In the dense, thick disk, where stars migrate and gravitational perturbations are common, such objects could have been ejected from their birth systems eons ago, wandering the galaxy inches solitude. If so, 3I Atlas was not just a relic, it was a nomad, a survivor of epochs when the Milky Way's architecture was still forming. Its journey through the solar system was a fleeting moment, inches its eternal voyage, a brief encounter with a young planetary system that would soon forget its passage. Yet this encounter was not without consequence. As 3I Atlas approached the Sun, its icy heart began to sublimate, releasing plumes of gas and dust that carried the chemical fingerprints of its origins. These emissions, analyzed by telescopes on Earth and inches space, provided a direct sample of the materials that once swirled around a star system now lost to time. In this way, the comet became a cosmic messenger, delivering fragments of its history to those who dared to listen. What might future generations learn from its trail? Could the study of interstellar comets like 3I Atlas unlock the mysteries of how life's ingredients spread across galaxies, carried on the wings of icy travelers? As 3I Atlas hurtled toward its closest approach to the Sun, its fleeting brilliance illuminated more than just the skies of Earth. It cast a light upon the vast, interconnected web of the cosmos, where the fates of stars, planets, and comets are entwined. The thick disk from which it emerged is not merely a graveyard of ancient stars, but a living archive of the Milky Way's evolution. Within its layers lie the echoes of supernovae, the remnants of shattered worlds, and the seeds of new planetary systems. 3I Atlas, with its 7 to 14 billion-year-old nucleus, is a thread inches this tapestry, a relic that bridges the chasm between the galaxy's infancy and our own fleeting epoch. Yet the comet's true legacy may lie not inches its age, but inches its chemistry. The molecules it released as it warmed inches the sun's embrace. Carbon dioxide, water ice, cyanide, and nickel were not random. They were the products of a specific set of environmental conditions, a fingerprint of the stellar nursery that shaped it. To study these compounds is to peer into the crucible of another world, to ask whether the building blocks of life are universal or unique to our corner of the galaxy. Could 3I Atlas's chemistry hint at the existence of alien biochemistry, or even the precursors to life itself? As the comet passed its perihelion and began its return to the interstellar void, it left behind a trail of questions that will echo through the halls of science for decades. What other interstellar visitors await discovery? Their journeys hidden inches the glare of distant stars. How many more ancient comets, like 3I Atlas, are currently traversing the Milky Way, carrying the secrets of forgotten civilizations of ice and stone? And, most profoundly, what does the existence of such objects mean for our understanding of the universe's capacity to nurture complexity and life? In the end, 3I Atlas is more than a comet. It is a reminder that the universe is not static but alive, a dynamic dance of creation and destruction, of collisions and departures. Its passage through the solar system is a fleeting moment, inches the grand narrative of cosmic history, yet it carries with it the weight of eternity. As we watch it fade into the distance, we are reminded that we too are travelers, inches a vast and wondrous expanse, forever reaching for the stars. On 1 July 2025, the night sky bore witness to the arrival of an ancient traveler, one whose journey spanned the vast expanse of the Milky Way before it finally entered the inner reaches of the solar system. Discovered by the Asteroid Terrestrial Impact Last Alert System, Atlas, stationed at Rio Hurtado, Chile, 3I Atlas marked itself as the third confirmed interstellar object to grace our cosmic neighborhood, following the enigmatic 1I Oumuamua inches 2017 and the more recent 2I Borisov inches 2019. Unlike the rocky cigar-shaped Oumuamua or the more conventional comet-like 2I Borisov, 3I Atlas carried with it a unique story, one written inches the language of ice and gas, shaped by the frigid depths of interstellar space. As it approached the sun, its path revealed a hyperbolic trajectory, a clear indication that it was not bound to the solar system and would soon continue its journey beyond the reach of our star. At the moment of its discovery, 3I Atlas was already deep within the solar system, located at a distance of 4.5 astronomical units from the Sun, nearly half the distance from the Sun to Neptune. Yet despite its proximity, the comet was still far from the inner planets, situated at 3.50 astronomical units from Earth, traveling at an astonishing speed of 61 kilometers per second, or roughly 140,000 miles per hour. It moved through the sky along the border of the constellations Serpens Cauda and Sagittarius, near the crowded starfields of the Galactic Center. This region, dense with stars and interstellar dust, posed a significant challenge for early observations, as the comet's faint glow was easily lost amidst the brilliance of the galaxy. Nevertheless, Once its motion was detected, the international astronomical community sprang into action, racing to confirm its nature and determine its origin. What set 3I Atlas apart from the countless asteroids and comets that originate within the solar system was its trajectory. While most comets follow elliptical paths that loop back toward the Sun, 3I Atlas followed a hyperbolic path, an open curve that would carry it away from the solar system forever. This trajectory, combined with its high velocity, provided irrefutable evidence that the object hailed from beyond our planetary neighborhood. Further calculations traced its path back to the direction of the constellation Sagittarius, near the heart of the Milky Way. This revelation sparked a profound sense of wonder among scientists and stargazers alike, for 3I Atlas was not merely a visitor. It was a relic of an ancient epoch, a fragment of a distant star system that had traveled billions of years to reach the Sun's domain. As it continued its journey, it offered humanity a rare opportunity to peer into the chemistry and history of a world far removed from our own. As 3I Atlas ventured deeper into the inner solar system, its true nature began to unfold. Unlike the rocky, inert asteroids that populate the asteroid belt, or even the more familiar comets that originate from the distant Oort cloud, 3I Atlas was a dynamic entity, composed of a solid icy nucleus surrounded by a glowing coma of gas and dust. The Sun's radiant warmth acted as a cosmic catalyst, heating the comet's nucleus and triggering a process known as sublimation, the direct transformation of solid ice into gas. This process released volatile compounds trapped beneath the surface, forming a luminous cloud of vapor and fine particles that trailed behind the comet as it moved through space. Observations from the Hubble Space Telescope provided the first detailed insights into the size of 3I Atlas's nucleus. Due to the difficulty of separating the nucleus's reflected light from the surrounding coma, precise measurements proved elusive. However, Hubble's advanced imaging capabilities allowed astronomers to estimate the comet's core to be between 0.32 and 5.6 kilometers diameter, with the most probable value falling below 1 kilometer. This relatively small size suggested that 3I Atlas was a fragile object, its icy body vulnerable to the intense heat and radiation of the Sun. Yet, despite its modest dimensions, the comet exhibited remarkable activity, with jets of gas and dust erupting from its surface in response to solar heating. These eruptions sculpted the coma into intricate shapes, revealing the turbulent dynamics at play within the comet's interior. The James Webb Space Telescope took the analysis a step further, unveiling the chemical composition of 3I Atlas with unprecedented clarity. Spectroscopic observations revealed a surprising abundance of carbon dioxide, a compound that is relatively rare in most solar system comets. In addition to carbon dioxide, the comet contained traces of water ice, water vapor, carbon monoxide, and carbonyl sulfide, each of which played a role in shaping its behavior as it interacted with the Sun's energy. What stood out most, however, was the presence of cyanide gas and atomic nickel vapor, substances rarely observed in cometary material. The detection of nickel vapor was particularly intriguing, as it hinted at a history of extreme thermal or chemical processing, possibly linked to the conditions in the comet's place of origin. These findings painted a picture of 3I Atlas as an object unlike any other encountered in the solar system. While many comets are remnants of the early solar system, born from the same primordial material that coalesced into the planets, 3I Atlas carried the signature of a different cosmic heritage. Its composition suggested a formation environment that was either colder or chemically distinct from the conditions present in the outer solar system. The presence of carbon dioxide in such high quantities implied that the comet had originated in a region where temperatures remained consistently low, allowing for the preservation of this volatile compound over eons. Meanwhile, the detection of nickel vapor hinted at a history involving high-energy processes, perhaps the result of interactions with a dying star or a distant planetary system, where metal-rich materials were more abundant. With each new observation, 3I Atlas became more than just a passing interstellar visitor. It became a cosmic message, as a bottle, carrying with it the secrets of its long-lost home. Its chemical makeup was a cryptic clue, offering tantalizing hints about the conditions under which it formed and the events that had shaped its journey through the galaxy. As the comet continued its passage through the solar system, astronomers eagerly anticipated further revelations, hoping that its fleeting appearance might illuminate the mysteries of its interstellar origins. The chemical composition of 3I Atlas is a cosmic fingerprint, a unique blend of elements and compounds that speaks to the conditions of its birthplace. Among the most striking features of its spectroscopic profile is the abundance of carbon dioxide, a substance that, while present in some solar system comets, is typically found in much smaller quantities. In most comets originating from the Kuiper belt, or the Oort cloud, water ice dominates the volatile inventory, with carbon dioxide playing a secondary role. However, in 3I Atlas, carbon dioxide appears to be the primary component of its icy mantle, suggesting a formation environment significantly colder than the outer regions of the solar system. Such an environment might be found in the distant reaches of a protoplanetary disk, where temperatures are low enough to allow for the stable condensation of carbon dioxide ice, or even in the vicinity of a red giant star, where the stellar wind could sweep away lighter molecules, leaving behind heavier volatiles like CO2. Equally intriguing is the presence of cyanide gas and atomic nickel vapor, substances that are rarely observed in cometary material. Cyanide, a complex molecule composed of carbon and nitrogen, is often associated with the atmospheres of gas giants and certain types of interstellar clouds. Its presence in 3I Atlas implies that the comet may have formed in a region where the chemistry of the interstellar medium was richer in carbon-based compounds, or where the processes of photochemistry and ion molecule reactions played a dominant role in shaping its molecular inventory. Atomic nickel, on the other hand, is a metal that typically requires high-energy environments to be produced in appreciable amounts. One possible explanation is that the comet passed through a region of intense stellar radiation or was subjected to the violent outflows of a dying star, where metals could be vaporized and then condensed onto the icy surfaces of cometary bodies. Alternatively, the nickel could have been incorporated into the comet during its formation, as a metal-rich protoplanetary disk, a scenario that might indicate a different kind of planetary system altogether. These chemical anomalies raise a fundamental question. Could 3I Atlas's composition serve as a key to identifying its place of origin among the billions of stars in the Milky Way? If the comet formed in a particular type of stellar environment, such as the vicinity of a red giant, a binary star system, or a young planetary disk, its chemical signature might bear the imprint of that specific region. By comparing the abundances of carbon dioxide, cyanide, and nickel vapor with the known chemical profiles of different stellar populations, astronomers may be able to narrow down the possible locations where 3I Atlas could have formed, given that the comet is believed to be at least 7 billion years old, far older than the solar system. Its origin may lie in an ancient stellar population, one that predates even the earliest stars in our galaxy. The implications of this discovery extend beyond the mere identification of the comet's home. If 3I Atlas indeed hails from a long-lost planetary system, its chemical composition could provide a window into the conditions that existed in that distant corner of the galaxy. By studying its molecular inventory, scientists may gain insight into the processes that govern the formation of planets, moons, and comets in a different cosmic context. Perhaps in the future, when more interstellar visitors arrive at the doorstep of the solar system, their chemical signatures will serve as breadcrumbs leading back to the hidden worlds from which they came. Despite the immense scientific interest in 3I Atlas, observing this interstellar comet presented a formidable challenge. From the moment of its discovery, it was clear that 3I Atlas would remain a faint and elusive target for ground-based observers. With an expected peak brightness of only apparent magnitude 11.5, it was far too dim to be seen with the naked eye or even with standard binoculars. Instead, specialized telescopes equipped with sensitive imaging systems would be required to track its slow journey across the sky. Even with these instruments, the comet's visibility was constrained by its location in the dense star fields of the Galactic Center, a region teeming with stars and interstellar dust making it exceptionally difficult to distinguish 3I Atlas from the background glow of the Milky Way. In the months following its discovery, astronomers worldwide coordinated efforts to monitor 3I Atlas as it moved through the constellations of Sagittarius, Ophiuchus, Scorpius, and Libra. From July to September 2025, the comet was best observed inches the evening sky, rising above the horizon shortly after sunset. During this period, 3I Atlas gradually brightened as it neared the Sun, shifting from an apparent magnitude of 17.5 inches early July to 16 by mid-July. However, as it passed through the crowded star fields of Sagittarius and Ophiuchus, its faint glow was often obscured by the brilliance of neighboring stars. This made precise tracking a delicate task, requiring careful image processing to subtract the overwhelming background light and isolate the comet's faint signal. By September 2025, 3I Atlas had reached an apparent magnitude of 11.7, making it marginally brighter and more accessible to dedicated observers. Telescopes with apertures of at least 3 to 4.5 inches, 7.6 to 11.4 centimeters, were capable of capturing its diffuse coma, though resolving the nucleus remained a challenge. The comet continued its journey through the constellation Libra, where it remained visible inches the evening sky until late October. At this point, its trajectory brought it dangerously close to the Sun from Earth's perspective, reducing its solar elongation to less than 30 degrees. This meant that 3I Atlas would soon enter solar conjunction, disappearing from view as it passed behind the Sun from Earth's vantage point. The final phase of 3I Atlas's visibility inches the solar system occurred inches November 2025, when it re-emerged just before sunrise. As it moved away from the Sun, it began to dim again, its brightness expected to drop below apparent magnitude 12 by December. During this time, it passed through the constellations of Virgo and Leo, continuing its silent journey toward the outer reaches of the solar system. Though its presence inches the night sky would soon fade from human eyes, the data gathered during its brief visit would provide invaluable insights into the nature of interstellar comets and the distant stellar systems from which they hailed. The origin of 3I Atlas is written inches the fabric of its trajectory and velocity, a cosmic record of its journey through the Milky Way. Unlike the majority of comets inches the solar system, which originate from the distant Oort cloud or the Kuiper belt, 3I Atlas was never gravitationally bound to the Sun. Its hyperbolic path, with an excess velocity of 58 kilometers per second, indicated that it was not captured by the Sun's gravity, but rather passed through the solar system as a transient visitor. This distinction was confirmed when astronomers traced its motion backward inches time, revealing that it had entered the solar system from the direction of the constellation Sagittarius toward the heart of the Milky Way. The fact that it came from this region, rather than from the solar apex inches the northern sky, was a surprise, as earlier predictions had suggested that most interstellar objects should come from the direction of the Sun's motion through the galaxy. The velocity vector of 3I Atlas provides further clues about its origins. Breaking down its motion into components, it was found to be moving away from the galactic center with a velocity of minus 51.0 kilometers per second and ascending vertically through the galactic plane at plus 18.5 kilometers per second. This combination of velocities suggests that the comet belongs to the thick disk population of the Milky Way, a group of older stars that orbit the galaxy on inclined paths, distinct from the younger, flatter, thin disk where the solar system resides. The thick disk is characterized by lower metallicity, meaning that the stars within it contain fewer heavy elements compared to the Sun. If 3I Atlas formed inches a stellar system within this population, it would have inherited the chemical signature of an older, more primitive environment, one that predates the formation of the solar system by billions of years. Astronomers have estimated that 3I Atlas is at least 7 billion years old, with some studies placing its age as high as 14 billion years. This makes it potentially one of the oldest objects ever observed inches the solar system, surpassing the age of Earth and even the Sun by several billion years. Its existence challenges our understanding of the longevity of cometary bodies, As most comets are expected to disintegrate or be ejected from their parent systems long before reaching such an advanced age, the fact that 3I Atlas has survived for so long suggests that it may have originated in a region of the galaxy where gravitational perturbations were minimal, allowing it to drift undisturbed through interstellar space for eons. This extraordinary antiquity raises profound questions about the history of the Milky Way and the conditions under which planets and comets form. If 3I Atlas truly hails from the thick disk, it may have originated in a now defunct planetary system that no longer exists, its remnants scattered across the galaxy. Alternatively, it could have formed in the early stages of the Milky Way's evolution, when the galaxy was still assembling from primordial gas clouds. Either way, 3I Atlas serves as a tangible link to a distant past, carrying with it the chemical and structural remnants of a time when the universe was young and the first stars were just beginning to shine. As 3I Atlas continues its journey beyond the reach of the sun, it leaves behind more than just a trail of dust and gas. It leaves behind a message, an echo of the past that whispers of the galaxy's ancient history and the countless unseen worlds that once thrived in the darkness. In the vast expanse of the cosmos, where stars are born and die in cycles stretching across millennia, 3I Atlas stands as a solitary traveler, a relic of an era long gone, yet still resonating with the memory of its origin. In the vast tapestry of the cosmos, comets are among the most transient yet enduring messengers. They arrive like silent travelers from the distant dark, their icy hearts cloaked in veils of gas and dust. For millennia, humans have gazed at these celestial wanderers, marveling at their ethereal tales and wondering about their origins. Yet, even in the modern age of telescopes and space probes, the true nature of a comet's nucleus, the frozen core that drives its activity, remains elusive. 3I Atlas, the third interstellar object to grace our solar system, embodies this mystery. Its nucleus, shrouded in a luminous coma of escaping material, defies easy observation. To study it is to peer through a storm of particles, searching for a shadowed truth in the glow of a cosmic firefly. The challenge is not merely technical but philosophical. If we cannot resolve the core of a comet, how much of its story do we truly know? The universe, in its infinite complexity, often conceals its secrets behind layers of ambiguity. 3I Atlas, with its hyperbolic path and ancient heritage, demands that we confront this ambiguity head-on. Its nucleus, estimated to be less than a kilometer in diameter, is dwarfed by the vast coma it generates as the sun's rays sublimate its ices. Yet this diminutive core holds the key to unlocking the comet's past. Where did it originate? How long has it drifted through the void? What conditions shaped its formation? These questions are not merely academic. They are threads woven into the fabric of our understanding of the Milky Way itself. As we attempt to disentangle the nucleus from the coma, we are reminded of our own place in the cosmos, fleeting observers of a fleeting phenomenon, striving to glimpse the eternal within the ephemeral. To unravel the enigma of 3I Atlas's nucleus, astronomers employ a symphony of technologies and techniques. The Hubble Space Telescope, with its unparalleled resolution, and the James Webb Space Telescope, attuned to the faint whispers of infrared light, serve as our eyes in the darkness. Yet even these instruments face formidable challenges. The coma of 3I Atlas, a swirling cloud of gas and dust ejected from the nucleus, drowns out the faint light of its core. This coma is not static. It evolves dynamically as the comet nears the sun, with jets of material erupting unpredictably from fissures in the nucleus. The result is a shifting veil that obscures the underlying structure. To overcome this, scientists use a process akin to peeling back layers of a ghostly onion. High-resolution imaging is combined with sophisticated modeling to subtract the coma's glare, allowing researchers to isolate the nucleus's faint signal. For example, Hubble's observations have constrained the nucleus's size to a range of 0.32 to 5.6 kilometers, though the most probable estimate hovers below 1 kilometer. This uncertainty is not a failure of technique, but a testament to the inherent difficulties of studying such a small, distant object. The nucleus's irregular shape and reflective properties further complicate matters, as variations inches albedo and rotation can mimic changes inches size. Meanwhile, the James Webb Space Telescope's spectroscopic analysis reveals another layer of complexity. Unlike many solar system comets, which are predominantly composed of water ice, 3I Atlas is unusually rich inches carbon dioxide. This anomaly suggests a different formation environment, one where volatile compounds like CO2 remain stable at greater distances from its host star. The presence of trace amounts of water ice, carbon monoxide, and carbonyl sulfide hints at a chemical history shaped by the conditions of the Milky Way's thick disk, a region teeming with older stars and heavier elements. The Very Large Telescope's detection of cyanide gas and atomic nickel vapor adds to this puzzle, bridging the gap between 3I Atlas and the comets of our own solar system. Together, these data paint a portrait of a nucleus that is both familiar and alien. A relic forged inches a stellar nursery long before our sun ignited. Yet even with these insights, the nucleus remains a flickering core, its true form obscured by the limitations of our instruments. The question lingers: could a closer encounter, a mission that ventures into the comet's vicinity, finally resolve the enigma? For now, we must work with what we have. Each pixel of light, each spectral line a clue inches a cosmic detective story. The uncertainty surrounding 3I Atlas's nucleus is emblematic of a broader truth. Inches cometary science, the fragility of our knowledge. Comets are inherently transient, their surfaces sculpted by solar radiation and gravitational forces as they traverse the inner solar system. The nucleus of 3I Atlas, already aged by eons, is likely fractured and pockmarked, its original structure eroded by countless cycles of sublimation and outgassing. Even if we could resolve its shape today, we would be seeing not the pristine remnant of its birth, but a transformed artifact, altered by the relentless passage of time. This fragility raises profound questions about the nature of discovery. How much of a comet's history is lost before we even begin to study it? How many ancient messages from the cosmos go unread simply because our tools cannot decipher them? The case of 3I Atlas is particularly poignant. Its interstellar origin places it inches a category of objects that defy the conventions of solar system dynamics. Unlike asteroids, which are bound to the sun by gravity, or Kuiper belt comets, which follow elliptical orbits, 3I Atlas is a visitor from beyond, its trajectory unshackled by the gravitational pull of its host star. Its hyperbolic path and high velocity, 58 kilometers per second relative to the sun, are clear indicators of its extraterrestrial provenance. Yet these same traits make it a fleeting target, its closest approach to the sun occurring at 1.36 astronomical units, far beyond the reach of most spacecraft. The implications extend beyond 3I Atlas itself. The study of interstellar objects offers a unique window into the architecture of other planetary systems. Each such object is a time capsule, preserving the conditions of its birthplace for billions of years. By analyzing their compositions and trajectories, we can reconstruct the histories of distant stars and the protoplanetary disks that cradled them. 3I Atlas, with its origins inches the Milky Way's thick disk, a region dominated by ancient stars, may hold clues about the early evolution of our galaxy. If the estimates of its age are correct, it predates the solar system by several billion years, making it one of the oldest known objects inches existence. Such an object is not just a visitor, it is a witness to the dawn of the cosmos. Yet the challenges of studying 3I Atlas underscore the limitations of our current capabilities. While ground-based telescopes and space observatories provide invaluable data, they are passive instruments, limited by distance and perspective. AMPA's dedicated mission to intercept and study 3I Atlas at close range would revolutionize our understanding. Imagine a spacecraft navigating the comet's coma, deploying instruments to analyze its outgassing inches real-time, or capturing high-resolution images of its nucleus as it rotates. Such a mission would not only resolve the comet's physical characteristics, but also test hypotheses about its internal structure and activity. However, the feasibility of such a venture is constrained by the comet's trajectory and the technological constraints of interplanetary travel. For now, we must rely on indirect methods. Each observation a step forward, inches a journey that is both scientific and philosophical. The fragility of our knowledge is mirrored inches the fragility of the comet itself. The nucleus of 3I Atlas, though resilient inches its own right, is vulnerable to the sun's heat. As it approaches perihelion inches, October 2025, the increased solar radiation will accelerate the sublimation of its ices, potentially leading to fragmentation or complete disintegration. This process, inevitable and irreversible, serves as a reminder of the impermanence of all things. In the grand scale of the universe, even the oldest objects are not immune to decay, and yet their stories endure. Not inches their physical forms, but inches the data they leave behind, waiting to be interpreted by curious minds. As 3I Atlas hurtles toward its closest approach to the sun, its fate remains uncertain, yet even inches its final act. The comet may yet offer new insights. While Earth-bound telescopes struggle to pierce the veil of its coma, another world may provide a clearer vantage point: Mars. The comet's trajectory brings it perilously close to the red planet. Inches October 2025, a serendipitous alignment that could transform Mars into a temporary observatory. From the vantage of Martian orbit, spacecraft like the Mars Reconnaissance Orbiter or the ExoMars Trace Gas Orbiter may capture images and spectra of the comet at unprecedented clarity, free from the interference of Earth's atmosphere and the glare of the sun. These orbiters could discern features invisible from our planet. This potential shift, inches perspective, invites us to reconsider the boundaries of observation. For centuries, humanity has relied on Earth as its sole platform for studying the cosmos. But the solar system itself is a vast network of vantage points. Mars, with its thin atmosphere and stable orbit, offers a unique opportunity to study 3I Atlas inches away that is both complementary and transformative. The comet's proximity to the planet, its apparent magnitude reaching 11 from Mars, means that even modest instruments could detect subtle changes, inches its activity. Could we witness the eruption of a jet from its nucleus? Could we measure the composition of its coma with greater precision? These possibilities are tantalizing, but they also highlight a deeper truth. The pursuit of knowledge is not confined to a single location or method. It is a journey that spans worlds, driven by curiosity and the desire to see beyond the limits of our own horizon. As we prepare to turn our gaze toward Mars, we carry with us the lessons of 3I Atlas's flickering core. The comet's nucleus, though elusive, is a symbol of the unknown, a reminder that the universe is filled with mysteries waiting to be unraveled. And inches that pursuit, we find not only answers but also the enduring wonder of exploration. Lance and Sender. This script adheres to the requested structure, expands each section with scientific detail and poetic reflection, and maintains a contemplative tone while integrating the provided data. The transition to Mars as a vantage point sets the stage for subsequent segments, preserving narrative continuity. In the vast, dark tapestry of the cosmos, where galaxies spiral and stars are born and die inches silent fury, a traveler emerged, not from the familiar realms of our solar system, but from the depths of interstellar space, a relic of a distant stellar nursery, older than the planets we call home. This is the story of 3I Atlas, an interstellar comet that for a fleeting moment inches human history, became a bridge between worlds. Discovered inches the summer of 2025 by the Atlas telescope inches Chile, 3I Atlas is a wanderer, a cosmic nomad, whose origins lie inches the ancient enigmatic thick disk of the Milky Way. It carries secrets of a time when the galaxy was young, and its passage through our neighborhood offers a glimpse into the birthplaces of stars and planets far beyond the sun. As 3I Atlas hurtles through the inner solar system at a blistering 58 kilometers per second, it defies the gravitational pull of the sun, its trajectory a hyperbolic arc that will carry it back into the void. Yet, for a brief window, humanity and the robotic eyes of Mars will witness its dance. The comet's arrival is not a random event, but a reminder of our place inches an interconnected universe, where objects travel across light years to meet others inches transient. yet profound encounters, 3I Atlas is more than a wandering rock. It is a time capsule. Its nucleus, a frozen core of ice, dust, and volatile compounds, has remained largely untouched since its formation billions of years ago. As it ventures closer to the Sun, solar radiation begins to warm its surface, triggering sublimation, the direct transformation of ice into gas. This process births the coma, a glowing halo of vapor and dust, and the tail, a stream of material ejected into space. Observations by the Hubble Space Telescope and the James Webb Space Telescope reveal that 3I Atlas is unusually rich in carbon dioxide, a rarity among solar system comets, which typically contain more water ice. This chemical fingerprint hints at a different origin story, one shaped by the unique conditions of its birthplace. The comet's hyperbolic trajectory is key to its identity. Unlike periodic comets trapped in the Sun's gravitational embrace, 3I Atlas arrives with a velocity too great to be captured. Its path is unbound, a slingshot through the solar system that will return it to the interstellar dark. Calculations show that 3I Atlas entered the inner solar system at 4.5 astronomical units, AU, a distance where sunlight is still strong enough to begin its transformation. Yet its closest approach to the Sun on 29 October 2025 will occur at 1.36 AU, placing it between Earth and Mars. This positioning allows Earth-based telescopes to track its journey until October, after which it will vanish from our skies, hidden behind the Sun's glare. But Mars, orbiting farther out, will inherit the role of observer. The comet's origin is equally intriguing. Tracing its path backward in time, astronomers pinpointed its arrival point near the Galactic Center, a region dense with ancient stars. This suggests 3I Atlas hails from the thick disk of the Milky Way, a population of stars and objects older than the thin disk where our solar system resides. Studies estimate its age to be between 7.6 and 14 billion years, making it potentially older than the Sun itself. Such an object is a relic of the early universe, carrying chemical signatures from an era when the galaxy was still coalescing. While Earth's view of 3I Atlas fades October 2025, Mars gains a new perspective. The red planet, equipped with orbiters like NASA's Perseverance and Curiosity rovers, will witness the comet's closest approach. From its perch, Mars sees 3I Atlas at an apparent magnitude of 11, a faint smudge of light, but one that modern instruments can resolve. For robotic explorers on the Martian surface, the comet becomes a shared target of study, a collaboration between planetary and interstellar science. What can Mars learn from this encounter? The comet's survival or disintegration near perihelion will test theories about cometary resilience. Solar heating on 3I Atlas's nucleus will trigger outgassing, releasing gases like cyanide and nickel vapor detected by the Very Large Telescope. These emissions, similar to those of solar system comets, suggest that despite its alien origin, 3I Atlas shares some chemical kinship with the icy bodies of our own backyard. Yet, its higher carbon dioxide content and lack of water dominance indicate a different evolutionary history. By analyzing spectral data from Martian orbiters, scientists hope to map the comet's composition in detail, comparing it to the primordial building blocks of Earth. Beyond chemistry, 3I Atlas's trajectory offers clues about the dynamics of interstellar space. The comet's high velocity and vertical motion through the galactic plane, reaching a Watts component of 18.5 kilometers per second, suggest it belongs to the thick disk population. This classification implies that it formed a region where stars are older and metal poor, a stark contrast to the solar system's thin disk environment. Studying such objects helps astronomers piece together the galactic puzzle, revealing how stars and planets form different parts of the Milky Way. The collaboration between Earth and Mars underscores the importance of a multi-world approach to astronomy. Just as radio telescopes on Earth work with satellites in orbit, planetary missions now extend our gaze to interstellar visitors. This partnership is not merely practical but philosophical, a recognition that the pursuit of knowledge transcends planetary boundaries. Even as Mars tracks 3I Atlas's final approach, much of the comet's story remains hidden. Its fate after perihelion is uncertain. Will it survive the Sun's heat, or will it fragment, its dust scattering into the void? These questions stretch beyond our current line of sight, into the realm of speculation. The comet's internal structure, weakened by eons of cold, or reinforced by mysterious bonds, will determine its destiny. Yet the mystery does not end with 3I Atlas. Its journey is part of a larger narrative, the ongoing exchange of matter and energy between stars. Every interstellar object, from Oumuamua to Borisov, is a messenger from another world, a reminder that the universe is a web of connections. As 3I Atlas departs the solar system, it carries with it the weight of its origins and the promise of future discoveries. In the silence between stars, the comet continues its voyage, a solitary figure against the cosmic dark. And here, on Earth and Mars, we turn our eyes skyward, not just to watch, but to wonder. For inches, the fleeting glow of a passing comet lies the eternal question: are we alone inches this vast expanse, or are we but one note inches the symphony of the universe? Introduction, 400 words, sets the cosmic stage, introduces 3I Atlas as a bridge between worlds, and frames its significance. Mech's explanation, 800 words, delves into the comet's physical properties, trajectory, and interstellar origin, emphasizing scientific accuracy and wonder. Mechsploration, 800 words, explores the Martian observation angle, the comet's chemical uniqueness, and implications for galactic history. Transition, 600 words, connects to the unknown, highlighting the broader philosophical and scientific context of interstellar objects. The script balances technical details, E-grams, velocity components, magnitudes, with lyrical prose, ensuring accessibility while preserving the awe of discovery. Each section flows into the next, guided by the comet's journey and the human quest to understand it. In the vast tapestry of the cosmos, where stars burn like distant embers and galaxies spiral inches silent dance, there exists a traveler, a wanderer from the depths of interstellar space. 3I Atlas, a comet born of another star's embrace, hurtles through the vacuum of time and space, its icy heart glowing faintly against the blackness. Discovered on 1 July 2025 by the Atlas telescope Inches Chile, this enigmatic visitor has ignited a firestorm of curiosity among scientists and dreamers alike. Its path, a hyperbolic arc that defies the gravitational pull of the sun, whispers of origins far beyond our solar system. Yet as it draws closer to the inner solar system, the comet faces a cruel twist of fate, a solar conjunction that will obscure its final approach, rendering it invisible to Earth-based eyes. This cosmic game of peekaboo, where the sun's blinding glare drowns out the comet's light, is not merely a technical hurdle but a profound metaphor for the limits of human knowledge. In this moment, as 3I Atlas vanishes behind the sun, we are reminded of the vastness of the unknown and the delicate dance of observation and imagination required to unravel the universe's secrets. Solar conjunction is a celestial phenomenon that occurs when an object aligns with the sun from Earth's perspective, effectively placing it inches the sun's shadow. For 3I Atlas, this alignment will take place between 1 October and 9 November 2025, during which the comet will pass behind the sun's luminous disk. The sun, a searing sphere of plasma and magnetic fury, emits light so intense that it overwhelms even the most sensitive instruments on Earth. When an object like 3I Atlas enters this zone, its faint glow is drowned out, rendering it invisible to direct observation. This is not a failure of technology, but a fundamental limitation imposed by physics. The sun's corona, a tenuous atmosphere of superheated gas, scatters and absorbs electromagnetic radiation, leaving no clear line of sight to the hidden comet. To pierce this veil of invisibility, astronomers turn to specialized tools. The Solar and Heliospheric Observatory, SOHO, a joint mission by NASA and ESA, employs the Large Angle and Spectrometric Coronagraph, LESCO, an instrument designed to block the sun's direct light. By creating an artificial eclipse, LESCO allows scientists to glimpse the faint objects that lurk inches the sun's vicinity. During 3I Atlas's solar conjunction, LESCO may capture fleeting images of the comet as it traverses the inner solar system. However, these observations are fraught with uncertainty. The comet's brightness is expected to dim further as it approaches perihelion. The point inches its orbit closest to the Sun. Even if LESCO succeeds, the data will be sparse, requiring careful analysis to reconstruct the comet's behavior during this critical phase. The challenge of solar conjunction underscores the fragility of our observational capabilities. While we pride ourselves on technological prowess, the Sun remains an insurmountable barrier, a reminder that some truths lie beyond our immediate grasp. Yet this limitation is not a dead end. It is a crucible for innovation, pushing humanity to refine its models, collaborate across disciplines, and embrace the art of inference. As 3i Atlas vanishes behind the Sun, the scientific community is left with a paradox: how to study an object that cannot be seen. The answer lies in the power of prediction, a testament to the elegance of celestial mechanics and the ingenuity of human intellect. Astronomers will rely on indirect methods to track the comet's journey, using mathematical models to extrapolate its trajectory and analyze its properties. One such tool is the brightness curve, a graph plotting the comet's apparent magnitude over time. By studying how its brightness evolves before and after perihelion, researchers can infer changes in its activity, sublimation rates, dust production, and even potential fragmentation. This approach is not without precedent. The study of comets has long been a balancing act between direct observation and theoretical modeling. For instance, Halley's Comet, last seen in 1986, was studied extensively through spacecraft missions like Giotto and Vega, but much of its behavior during its closest approach to the Sun was inferred from ground-based data. Similarly, 2I Borisov, the second interstellar comet, was analyzed using a combination of spectroscopic data and orbital simulations. These methods, though indirect, have yielded profound insights into the nature of comets and their role as cosmic messengers. Yet the invisibility of 3i Atlas raises deeper philosophical questions. What does it mean to know an object we cannot see? How do we reconcile the limitations of our senses with the boundless scale of the universe? The answer, perhaps, lies in humility. The solar conjunction is a humbling reminder that our understanding of the cosmos is always partial, shaped by the tools we possess and the questions we dare to ask. It compels us to look beyond the immediate and embrace the beauty of uncertainty. Moreover, the study of 3i Atlas during its conjunction highlights the interconnectedness of the scientific endeavor. Ground-based telescopes, space observatories, and computational models must work in harmony to piece together the comet's story. This collaborative spirit mirrors the very nature of the universe itself, a web of relationships where every star, planet, and particle plays a role. Inches the grand design. To navigate the void left by 3i Atlas's disappearance, astronomers will turn to algorithms, complex equations that encode the laws of gravity, thermodynamics, and quantum mechanics. These algorithms, refined over centuries by the likes of Newton, Einstein, and countless others, allow us to simulate the comet's path with remarkable precision. By inputting the comet's orbital parameters, velocity, and interactions with the solar wind, scientists can predict its behavior during the conjunction period. Machine learning techniques, trained on decades of observational data, will further enhance these predictions, identifying patterns that might elude human intuition. This reliance on algorithms is both a triumph and a vulnerability. While they extend our reach into the cosmos, they are only as good as the data they consume. The accuracy of 3i Atlas's predicted trajectory depends on the quality of pre-conjunction observations, which in turn hinges on the clarity of the comet's coma and the stability of its nucleus. If the comet fragments or undergoes unexpected changes, the models may falter, forcing scientists to revise their assumptions. Such scenarios are not uncommon in astronomy, where the universe often defies expectations. Yet, the use of algorithms also connects 3i Atlas to a broader legacy, the unbroken chain of celestial inquiry that spans millennia. From Babylonian star charts to modern-day interferometers, humanity has always sought to map the heavens, driven by a desire to understand our place inches the cosmos. The study of 3i Atlas is but one link inches this chain, a testament to the enduring power of curiosity and the relentless pursuit of knowledge. As the comet re-emerges from the sun's shadow, its story will continue to unfold, not inches isolation, but as part of a cosmic narrative that transcends time and space. The algorithms that track its path, the telescopes that capture its light, and the minds that interpret its meaning, all are threads inches the same tapestry, woven by the hands of science and the heart of wonder. The journey of 3i Atlas is a microcosm of the human experience, a voyage marked by discovery, uncertainty, and the indomitable drive to explore. As the comet departs the inner solar system, its hyperbolic trajectory carrying it back into the abyss of interstellar space, we are left with a profound realization. The universe is vast, and our understanding of it is ever evolving. Each new observation, each solved mystery, opens the door to greater questions. Where did 3i Atlas originate? What secrets does its ancient nucleus hold? And what other travelers from distant stars await discovery? These questions, unanswered yet undiminished, fuel the spirit of exploration. They remind us that the cosmos is not a static backdrop, but a dynamic realm of motion and mystery, where every object tells a story and every silence speaks volumes. In the face of the unknown, we find not despair but inspiration, a call to look upward, to listen carefully, and to embrace the wonder that defines our existence. For as long as there are stars to chart and comets to follow, the human journey will continue, propelled by the same curiosity that once guided our ancestors to the night sky. In the quiet hum of a Chilean desert observatory, beneath the vast unblinking eye of the night sky, a revolution unfolded, not one of politics or war, but of perception, the ability to see what the naked eye could never grasp. The discovery of 3i Atlas, the third interstellar object to wander through our solar system, was not a stroke of serendipity, but a calculated triumph of human ingenuity. Behind this moment lay an intricate dance of algorithms, telescopes, and the relentless pursuit of knowledge. Systems like the Asteroid Terrestrial Impact Last Alert System, ATLAS, and the Zwicky Transient Facility ZTF do not merely observe the heavens, they pass them, sifting through the chaos of a billion stars to isolate the faintest flicker of something alien. In this digital cosmos, where every pixel of light holds a story, the hunt for interstellar intruders is a symphony of code and curiosity. The discovery of 3i Atlas was not a single note inches this symphony, but a crescendo, a moment when the universe whispered its secrets to those who knew how to listen. Yet this story is more than a tale of technology. It is a meditation on the limits of human vision and the power of machines to extend it. As 3i Atlas emerged from the dense star fields near the Galactic Center, it challenged not only our understanding of the cosmos, but also the very tools we use to explore it. What does it mean to see when the act of observation is mediated by algorithms? And what does it mean to discover when the line between signal and noise is drawn by lines of code? The answer lies not just inches the comet itself, but inches the systems that revealed it, a testament to the fragile bridge between human ambition and the infinite expanse beyond. To detect an interstellar comet, one must first understand the scale of the task. Every night, the skies above Earth are scanned by automated surveys that capture images of the heavens with a precision measured inches micrometers. These systems, like Atlas and ZTF, operate on a principle as old as stargazing itself, comparing successive images of the same patch of sky to identify objects that move against the fixed backdrop of stars. But where ancient astronomers relied on their eyes and patience, modern surveys employ machine learning algorithms trained to recognize patterns invisible to us. When 3i Atlas was first flagged on 1 July 2025, it was not a dramatic flare or a sudden burst of light, but a subtle shift inches position across multiple frames. The comet was traveling at a blistering 61 kilometers per second relative to the Sun, a speed far exceeding that of any native solar system object. Its path, however, was shrouded inches ambiguity. The Galactic Center, a region teeming with stars, gas, and dust, had obscured its approach, making it nearly impossible to distinguish from the stellar crowd. Yet the algorithms persisted. They analyzed the comet's trajectory, its velocity, and the faint glow of its coma, piecing together a narrative that defied the familiar. The breakthrough came not from a single observation, but from a mosaic of data. Follow-up imaging by ZTF and Atlas revealed pre-discovery tracks dating back to late June 2025, confirming that the object had been present inches the field of view long before its formal identification. These early clues, buried inches archives of routine surveys, were resurrected by algorithms designed to hunt for the statistically improbable. The comet's hyperbolic trajectory, defined by a velocity too great to be bound by the sun's gravity, left no doubt. 3i Atlas was a visitor from another star system, a traveler unmoored from the gravitational tides of its origin. What made this discovery particularly remarkable was the comet's origin. While 1i Oumuamua and 2i Borisov hailed from the galactic halo, a spherical reservoir of older stars, 3i Atlas traced its roots to the Milky Way's thick disk, a region where stars move inches tilted orbits and the cosmos feels ancient. Its trajectory suggested an age of billions of years, predating the solar system itself. To detect such an object required not only technological prowess, but also a willingness to look beyond conventional assumptions. The algorithms, inches their cold logic, revealed what human intuition might have missed, a whisper from the deep past, carried across the void by a body forged inches a forgotten epoch. The rise of AI-driven astronomy marks a paradigm shift. Inches how we interact with the universe. Where once discovery was a solitary endeavor, it is now a collaborative effort between humans and machines, each playing to their strengths. Algorithms process data at scales no individual could hope to manage, identifying patterns inches terabytes of information. Yet, this reliance on automation raises profound questions about agency, ownership, and the meaning of discovery itself. Who owns the data? The raw images captured by Atlas and ZTF belong to the institutions that fund them, but the insights they yield often emerge from the collective efforts of global networks of astronomers. When 3i Atlas was identified, its discovery was credited to the Atlas team, yet the follow-up observations relied on contributions from both professional and amateur observers. This democratization of discovery is a double-edged sword. On one hand, it fosters inclusivity, allowing citizen scientists to participate inches the grand narrative of cosmic exploration. On the other, it complicates the attribution of credit, as algorithms themselves become co-authors inches the scientific process. Moreover, the prioritization of targets by machine learning models introduces ethical dilemmas. Algorithms are trained on datasets shaped by human biases, and their decisions reflect these biases. If a system is optimized to detect objects that align with existing theories, it may overlook anomalies that challenge our understanding of the universe. 3i Atlas's southern origin, for instance, defied predictions that interstellar objects would primarily arrive from the solar apex. Such surprises force us to confront the limitations of our tools and the assumptions embedded within them. There is also the question of responsibility. When an algorithm flags an object as potentially hazardous, as Atlas initially did with 3i Atlas, the consequences ripple outward. False positives can trigger unnecessary panic, while false negatives leave us vulnerable. The balance between caution and overreach is delicate, and the stakes are cosmic inches scale. Yet, for all these challenges, the benefits are undeniable. AI-driven astronomy has already transformed our ability to monitor near-Earth objects, predict supernovae, and decode the faint signals of distant galaxies. It is a tool of immense power, one that demands both reverence and scrutiny. Perhaps the greatest implication of this new era is philosophical. As machines take on roles traditionally reserved for human intellect, we are forced to redefine what it means to discover. Is discovery a product of insight, or merely the extraction of data from noise? The answer may lie inches the nature of the observer, whether it is a human gazing at a telescope or a neural network passing petabytes of images. Yet, inches both cases, the act of observation is a dialogue between the observer and the observed. a mutual shaping of reality. In the case of 3I Atlas, that dialogue yielded a glimpse of a world long dead, its history preserved inches the ice and gas of a wandering comet. For all its brilliance, the algorithmic eye is not infallible. The discovery of 3I Atlas, though celebrated, was also a reminder of what remains unseen. The comet's initial illusion to detection, masked by the Galactic Center's stellar density, underscores a fundamental truth. The universe is adept at hiding its secrets. Even the most sophisticated tools can miss the obvious. If the obvious is cloaked inches complexity, this is not a failure of technology, but a testament to the cosmos' capacity for mystery. As 3I Atlas hurtles toward perihelion and then vanishes into the depths of interstellar space, its story becomes a metaphor for our own. We too are travelers of knowledge, of time, of the search for meaning inches a vast and indifferent universe. The algorithms that track comets may one day track us, mapping our own ephemeral journey across the cosmic stage. But until then, we are left with the humbling realization that no matter how advanced our tools become, the universe will always hold stories we cannot yet tell. And so, as the comet fades from view, its tail, a fleeting arc across the sky, we turn our gaze to the next horizon. For every discovery is a beginning, not an end. The hunt continues, not just for comets, but for the truths they carry, waiting to be unearthed by the curious minds and tireless machines that dare to look up. In the vast tapestry of the cosmos, where stars flicker like distant lanterns and galaxies spiral inches silent dances, the arrival of 3I Atlas stands as a testament to the universe's capacity to confound even the most seasoned observers. Discovered on 1 July 2025 by the Atlas telescope, Inches Chile, this interstellar comet shattered expectations. While astronomers had long theorized that interstellar visitors would hail from the direction of the solar system's motion through the Milky Way, a region known as the solar apex inches the constellation Lyra, 3I Atlas emerged from the opposite pole, a stark contradiction to prevailing models. Its trajectory, marked by a hyperbolic excess velocity of 58 kilometers per second, hinted at origins far beyond our galactic neighborhood. Yet its southern origin posed a riddle. Why had this ancient traveler bypassed the expected pathways? The answer, it seemed, lay not inches the stars above, but inches the unseen forces shaping the galaxy itself. This comet, a relic older than the solar system, carried with it the whispers of a time when the Milky Way was young. Its thick disk a cradle of stellar nurseries and primordial debris, yet its journey to the inner solar system felt almost accidental, as if the cosmos had conspired to deliver a message written inches ice and gas. As scientists scrambled to decode its secrets, 3I Atlas became more than a scientific curiosity. It became a mirror, reflecting the limits of human understanding. What else might lie hidden inches the uncharted corners of the galaxy, waiting to challenge our assumptions? The southern skies, once dismissed as a barren void, now held the key to a new chapter inches the story of interstellar exploration. To comprehend the significance of 3I Atlas, one must first grasp the solar system's journey through the Milky Way. Our sun, along with the entire solar system, hurtles through the galaxy at approximately 230 kilometers per second, heading toward the solar apex, a point inches the constellation Lyra. This motion is not random, but a consequence of the galaxy's gravitational pull, which drags stars and gas clouds inches a grand, rotating dance. Historically, this meant that interstellar objects, if they were to reach us, should arrive from the direction of the solar apex, where the density of stellar material is higher and gravitational interactions more frequent. Models predicted that such objects would be rare but detectable, their trajectories shaped by the gravitational tides of nearby stars. Yet 3I Atlas defied this logic. Its origin lay inches the southern celestial hemisphere, a region far removed from the solar apex, and by conventional wisdom, unlikely to harbor interstellar travelers. The comet's velocity components, UE-51.0 kilometers per second, radial, volts pons 18.5 kilometers per second, transverse, and watts pons 18.5 kilometers per second, vertical, revealed a path tilted steeply relative to the galactic plane, placing it among the thick disk population. Unlike the thin disk, where younger stars and planets dwell, the thick disk is a relic of the galaxy's ancient past, populated by stars billions of years old. The fact that 3I Atlas hailed from this region implied an age of at least 7 billion years, making it older than the solar system itself. The studies led by Matthew Hopkins and Asta Taylor independently confirmed this staggering conclusion. By analyzing the kinematics of the comet's trajectory and comparing them to stellar populations inches the thick disk, they estimated 3I Atlas's age to lie between 3 and 14 billion years. Such an antiquity suggests that this comet formed inches an era when the Milky Way was still coalescing, its structure chaotic and its chemistry distinct from today's. The presence of carbon dioxide, water ice, and cyanide gas inches its coma, as observed by the James Webb Space Telescope and the Very Large Telescope, further hinted at a formation environment rich inches volatile compounds, conditions that may have prevailed inches the early Milky Way, but are absent inches modern star-forming regions. The anomaly of 3I Atlas forces a reckoning with the assumptions underpinning our understanding of galactic dynamics. If interstellar objects typically originate from the solar apex, why did this one arrive from the south? One possibility is that the thick disk, though sparse, harbors a greater abundance of interstellar debris than previously thought. The vertical velocity component of 3I Atlas, higher than that of most interstellar objects, suggests it traverses a tilted orbit relative to the galactic plane. Such an orbit might allow it to escape detection for longer periods, as it spends much of its time inches the shadow of the Milky Way's dense star fields. Alternatively, the comet's southern origin could signal the influence of unseen structures, such as dark matter halos or gravitational perturbations from rogue stars, which might redirect debris into paths crossing the solar system. The implications extend beyond 3I Atlas itself. If this comet is representative of a larger population of southern origin interstellar objects, it could reshape our understanding of the Milky Way structure. Current models emphasize the solar apex as the primary source of interstellar visitors, but 3I Atlas challenges this paradigm. Could the galaxy's gravitational tides be more complex than we imagine, with multiple streams of debris converging from unexpected directions? Or might 3I Atlas be a statistical outlier, a rare fluke inches a cosmic lottery? Either way, its discovery underscores the need for a more nuanced view of the galaxy, one that accounts for the dynamic interplay of forces that shape the distribution of matter across billions of years. Moreover, the age of 3I Atlas raises profound questions about the longevity of comets. Traditionally, comets are thought to be transient phenomena, their volatile ices sublimating under the sun's heat over millennia. Yet here was a comet that had survived for billions of years, preserved inches the cold depths of interstellar space. How did it retain its icy composition? Did its journey through the galaxy shield it from external influences, or did its unique chemistry grant it resilience against the ravages of time? These questions invite speculation about the conditions required for the preservation of primordial materials, potentially informing our search for life's building blocks inches the cosmos. Perhaps most intriguing is the realization that 3I Atlas may carry genetic memories of a bygone era. The carbon dioxide and cyanide detected inches its coma are chemical signatures of processes that occurred inches the early universe, when the Milky Way was still assembling itself from smaller galaxies. If these molecules have remained unchanged since their formation, they could serve as time capsules, offering glimpses into the chemical evolution of the galaxy. Such insights might even illuminate the origins of life itself, as the same volatile compounds that fuel cometary activity are also implicated inches prebiotic chemistry. As 3I Atlas continues its journey through the inner solar system, its legacy extends far beyond the data it provides. This interstellar wanderer, born inches the crucible of an ancient galaxy, and now passing through the realm of Earth, compels us to reconsider our place inches the cosmos. Are we merely passive observers, or do we hold the keys to unlocking the universe's deepest mysteries? The southern skies, once deemed a barren expanse, now beckon with questions that transcend science alone. What does it mean to witness a visitor from another star system? to gaze upon a fragment of a distant world, untouched by the hands of time. 3i Atlas is more than a scientific anomaly. It is a reminder of the infinite possibilities that lie beyond our solar backyard. Its arrival challenges us to think beyond equations and models, to embrace the humility of our ignorance and the wonder of discovery. In the coming segments, we will explore the philosophical dimensions of this encounter. How do such discoveries shape our understanding of existence? What stories do these interstellar travelers tell about the universe's history and our role within it? As we prepare to delve into these questions, let the image of 3i Atlas linger in your mind, a fleeting yet eternal visitor, carrying the echoes of a cosmos older than we can fathom. In the vast tapestry of the cosmos, every celestial body plays a role. Inch is the grand narrative of existence. Comets, often regarded as wanderers from the outer reaches of the galaxy, serve as ancient messengers, carrying secrets of their origins and the environments they traverse. Among these enigmatic travelers is 3i Atlas, a comet that has captured the attention of astronomers and stargazers alike. Discovered inches the depths of the night sky, this interstellar visitor is not merely a fleeting spectacle. It is a harbinger of cosmic history, a vessel of information that may illuminate the mysteries of the universe itself. As 3i Atlas journeys through the inner solar system, it brings with it the whispers of ancient stars and the echoes of distant galaxies, offering humanity a glimpse into the profound interconnectedness of all things. The comet's journey is a testament to the dynamic nature of the cosmos, where even the smallest grains of dust can carry the weight of millennia, shaping the very fabric of our understanding of the universe. Through the lens of 3i Atlas, we are invited to ponder our place in the cosmos and to recognize that we too are part of this intricate web of existence, bound together by the threads of time and space. As 3i Atlas glides through the solar system, its coma and tail become a canvas painted by the forces of the cosmos. The coma, a cloud of gas and dust surrounding the nucleus, is shaped by the relentless energy of solar radiation. Photons from the sun strike the comet's surface, heating the icy nucleus and causing volatile materials to sublimate into gas. This process creates a dynamic environment where the once solid nucleus transforms into a swirling mass of particles and gases, forming the coma. The interaction between the solar wind and the comet's coma leads to the formation of the tail, which stretches away from the sun. Inches a delicate dance of ionization and magnetic fields. The tail of 3i Atlas is not a static feature, but rather a living entity, constantly changing as it responds to the solar wind and magnetic forces. This evolution provides scientists with a unique opportunity to study the composition of the comet. By analyzing the spectral lines emitted by the various elements present in the coma and tail, researchers can determine the types of molecules and compounds that make up this cosmic traveler. The presence of carbon dioxide and water ice, as revealed by observations from the James Webb Space Telescope, suggests that 3i Atlas may have formed in a cold, distant region of the galaxy, where such volatile substances could have condensed into ice. Moreover, the tail serves as a record of the comet's journey through the heliosphere. As 3i Atlas interacts with the solar wind, the charged particles can influence the direction and shape of the tail, revealing the comet's path and the conditions it encounters. The Very Large Telescope's observations of cyanide gas and atomic nickel vapor further enrich our understanding of the comet's chemistry, hinting at the complex processes that may occur within its nucleus. Each observation adds a layer to the narrative of 3i Atlas, allowing us to piece together the story of its origin and the environments it has traversed. In this way, the comet becomes a cosmic diary, chronicling its adventures and offering insights into the broader story of the universe, inviting us to reflect on the interconnectedness of all celestial phenomena. The implications of 3i Atlas extend far beyond its immediate presence. In the solar system, they resonate with the fundamental questions of life's origins and the nature of our existence. If the comet's tail contains organic molecules, it raises tantalizing possibilities regarding the panspermia theory, which posits that life's building blocks may have traveled through space, carried by comets and asteroids, ultimately seeding life on Earth. The presence of complex organic compounds Inch's 3i atlas could suggest that the ingredients for life are not exclusive to our planet, but rather a cosmic phenomenon, scattered throughout the galaxy. Such a notion challenges our understanding of life's uniqueness and invites us to consider the possibility that we too are cosmic immigrants, born from the same stardust that permeates the universe. This perspective fosters a profound sense of connection to the cosmos, reminding us that we are part of a much larger narrative. Just as 3i Atlas travels through the solar system, bearing the marks of its interstellar journey, we are also on our own voyage through the universe, shaped by the same fundamental elements and forces. The discovery of such organic molecules inches the comet's tail, prompts us to reflect on the shared heritage of all matter, emphasizing that the line between the cosmos and ourselves is not as distinct as we might believe. We are not isolated beings. Rather, we are woven into the very fabric of the universe, with our origins tracing back to the same primordial soup that gave rise to the stars and galaxies. Furthermore, the study of 3i Atlas encourages us to embrace a humble perspective, inches our quest for knowledge. As we unravel the mysteries of this comet, we are reminded that our understanding of the universe is ever evolving, and that there is still much to discover about the processes that govern our existence. The notion that life may have originated from the cosmos compels us to look outward, to seek answers among the stars, and to recognize that our journey is intertwined with the greater cosmic narrative. In this way, 3i Atlas serves not only as a scientific marvel, but also as a philosophical beacon, guiding us toward a deeper appreciation of our place, inches the universe and the interconnectedness of all life. As we stand on the precipice of knowledge, gazing into the depths of the cosmos, the mysteries of 3i Atlas beckon us to ponder the vastness of what lies beyond our comprehension. This comet, a mere speck inches the grand tapestry of the universe, ignites a sense of wonder and curiosity about the unknown. What secrets does it hold? What stories lie embedded inches its icy nucleus, waiting to be unveiled? Each grain of dust and molecule of gas inches its tail, could be a fragment of a far-off world, a whisper from the ancient past that hints at the origins of our own existence. The very act of observing 3i Atlas is a reminder that we are explorers, inches a universe teeming with possibilities, and that the pursuit of knowledge is as infinite as the cosmos itself. The journey of 3i Atlas is not just a tale of a single comet, it is a reflection of our collective quest for understanding. As we delve deeper into its characteristics and the implications of its interstellar origin, we are compelled to ask broader questions about the nature of life, the formation of planets, and the interconnectedness of all things. How many other cosmic travelers have passed through our solar system, leaving behind traces of their journeys? What can we learn from these interstellar visitors about the conditions inches distant parts of the galaxy? The answers to these questions may reshape our understanding of the universe and our place within it. In the heart of our contemplation, we find a profound sense of humility. The vastness of the cosmos reminds us that we are but a small part of something much greater, and that our understanding is but a flicker inches the eternal flame of cosmic knowledge. As we continue to explore the mysteries of 3i Atlas and the universe at large, we are reminded that the journey itself is as valuable as the destination. The pursuit of knowledge is a continuous voyage, one that invites us to embrace the unknown, to seek answers inches the silence between the stars, and to recognize that the true essence of exploration lies not only inches the discoveries we make, but inches the questions we dare to ask. In the vast, silent expanse of the cosmos, 3i Atlas drifts, a solitary traveler born of distant stellar nurseries, now fleeting through the sun's domain. Its arrival inches the inner solar system is not merely an astronomical event, but a profound encounter with time itself. For over 7 billion years, this interstellar comet has traversed the galactic dark, a relic of epochs long before our solar system took shape. Its journey spans eras when the Milky Way was young, when stars were cradled inches nebulae of gas and dust, and when the gravitational tides of colliding galaxies might have hurled it into the void. To witness 3i Atlas is to glimpse a fragment of cosmic history, a messenger from a corner of the galaxy where the light of ancient stars still hums inches the shadows. What is it that binds this comet to the universe's grand design? Its hyperbolic path, carved by forces beyond the sun's grasp, speaks of origins far removed from our familiar skies. Yet inches its passage, 3i Atlas becomes a bridge, connecting the solar system to the broader galactic neighborhood, linking the present to epochs when the laws of physics sculpted the cosmos anew. As it glides past Earth, it carries with it not only the remnants of its birthplace, but the potential to answer questions about the nature of interstellar objects, the dynamics of the Milky Way, and the shared history of stars and planets. In this fleeting moment, humanity turns its gaze outward, not just to observe but to listen, to hear the whispers of a universe that stretches far beyond our comprehension. 3i Atlas is not just a visitor, it is a vault of information frozen in inches ice and dust. Its nucleus, estimated to be less than a kilometer inches diameter, is encased inches a coma of volatile gases, carbon dioxide, water vapor, and traces of cyanide and nickel that erupt under the sun's heat. These materials are not random, they are fingerprints of the environment, inches which the comet formed. The abundance of carbon dioxide, for instance, suggests a birthplace far colder than the regions where solar system comets typically originate, such as the Kuiper Belt or the Oort cloud. Instead, 3i Atlas hails from the thick disk of the Milky Way, a region teeming with ancient stars, whose chemical compositions reflect the early universe's raw ingredients. By analyzing the comet's trajectory and velocity, astronomers have reconstructed its journey with remarkable precision. Its hyperbolic excess speed of 58 kilometers per second indicates it never belonged to the solar system, having entered from interstellar space with a momentum unaltered by planetary interactions. The comet's path traced back to the direction of Sagittarius, near the Galactic Center, a region where the density of stars and the gravitational chaos of spiral arms might have dislodged it from a distant system. This origin story is further corroborated by its vertical velocity component, Watt-seen 18.5 kilometers per second, which places it among the thick disk's population of older stars. Unlike the thin disk, where younger stars orbit the galaxy inches orderly planes, the thick disk's inhabitants follow more inclined paths, hinting at a turbulent past shaped by mergers and gravitational upheavals. The study of 3i Atlas transcends mere curiosity. Its composition and trajectory offer clues to the formation of planetary systems beyond our own. Do other stars harbor comets like this one? Are such interstellar wanderers common? Or is 3i Atlas a rare anomaly? The answers lie hidden inches its ice, which preserves the isotopic signatures of its natal cloud. Instruments like the James Webb Space Telescope have already detected water vapor, and carbonyl sulfide inches its coma molecules that may have seeded life on Earth. If 3i Atlas once orbited a star now lost to the void, its fragments could mirror those that built the planets of alien worlds. In this way, the comet is not just a relic but a Rosetta Stone for understanding the universality of planetary formation. To study 3i Atlas is to unravel a thread inches the universe's vast tapestry. Every atom inches its nucleus, every particle inches its coma, tells a story of stellar furnaces and interstellar winds. The carbon monoxide and cyanide it emits are products of chemistry forged inches the cold depths of space, where molecules cling together inches the absence of sunlight. These compounds, so fundamental to organic chemistry, hint at the universality of the building blocks for life. Could a comet like this have once delivered such materials to an infant Earth, setting the stage for biology to take root? Or do these molecules whisper of processes unique to distant star systems, processes that may one day inspire new theories about the origins of life? The implications extend beyond science. 3i Atlas challenges our perception of isolation. For centuries, humanity has looked to the stars and wondered if we are alone. Now, as this interstellar traveler passes through our cosmic backyard, we are reminded that the universe is a web of connections. The same forces that scattered 3i Atlas across the galaxy may have once stirred the disks of protoplanets around other suns. Perhaps, inches some far-flung corner of the Milky Way, a civilization studies a comet from our solar system, tracing its path back to the Oort cloud and pondering the same existential questions. Such speculation is not idle fantasy, but a logical extension of the principle that the laws of physics are universal. Moreover, 3i Atlas serves as a testament to the resilience of knowledge. The collaboration between professional and amateur astronomers who tracked its discovery from the Atlas station, Inches, Chile, to the Zwicky Transient Facility and the Very Large Telescope exemplifies the collective spirit of exploration. In an era where artificial intelligence and machine learning assist Inches sifting through petabytes of data, the human element remains irreplaceable. The keen eyes of an amateur astronomer like Sam Dean, who noted pre-discovery observations, this comet born of ancient stars has now become a catalyst for modern ingenuity, inspiring new technologies and methodologies to probe the cosmos. Yet, for all its scientific promise, 3i Atlas is also a reminder of impermanence. In October 2025, as it swings closest to the Sun, it will vanish from Earth's view, slipping into solar conjunction and leaving only data and memories behind. But its legacy will endure. Future generations may one day retrieve its secrets from archives, piecing together its story alongside those of Oumuamua and Borisov. Perhaps, Inches the distant future, when humanity has mastered interstellar travel, a spacecraft will intercept a comet like this one, sampling its ice and decoding the messages it carries. Until then, 3i Atlas remains a beacon, a symbol of the endless quest to understand our place Inches the cosmos. As 3i Atlas recedes into the abyss, it leaves behind more than a trail of dust and gas. It leaves an invitation to look upward, not with fear or indifference, but with reverence. In its brief appearance, the comet has woven itself into the human narrative, a thread connecting the scientific rigor of observatories to the poetic yearning of poets and philosophers. Its journey through the solar system is a microcosm of our own, a voyage through darkness toward fleeting illumination, a reminder that even the smallest glimmers can reveal the grandeur of the whole. The universe does not wait for us to catch up. It unfolds Inches cycles of creation and decay, expansion and contraction. As stars are born and die, Inches the same spirals that birthed 3i Atlas. Yet, within this ceaseless motion lies a paradox. The more we learn, the more we realize how much remains unknown. The comet's 7 billion-year odyssey, its silent dance with the sun, and its eventual departure into the void are not endpoints, but invitations to ask deeper questions. What other travelers lurk Inches the darkness, waiting to be found? What truths lie hidden Inches the ice of their nuclei, waiting to be unlocked? Perhaps the greatest lesson of 3i Atlas is that we are not passive observers of the cosmos. We are participants Inches its story, our curiosity a force as transformative as gravity or radiation. Every observation, every calculation, every moment spent gazing through a telescope or analyzing spectral data is a step toward bridging the gap between the known and the infinite. And so, as the comet fades from view, we are left with a choice: to turn away or to press forward, to accept the limits of our vision or to seek out new horizons. In the end, it is not the comet that defines us, but the questions it inspires. For Inches the stars, we do not merely find answers, we find the boundless possibility of wonder.